will take you one more step further in the course, because after a break, your mind is fresh enough to appreciate it. So if you did the quite unpleasant work of implementing the layout optimizations that I have discussed, you may realize that the performance is not what you would expect compared to the amount of effort that you have put into it. And this leads us to talk about one unfortunate concern when using high-level languages that try to compile to efficient low-level code, like Rust and C++. And that concern is inlining. It has been said before by C++ designers that C++ has zero-cost abstractions, in the sense that you have nice abstractions, yet the performance is as good as if you had written the thing yourself, and if you don't use it, you don't pay for it. Unfortunately, that's a lie, unless the compiler helps you. For so-called zero-cost abstractions to work, you vitally depend on compilers to do one specific kind of optimization, which is called inline expansion or inlining, and which is basically, when you call a function, instead of actually calling the function, the generated code just copy-pastes the content of the function into the caller, and then specializes the code based on the context in which it's been called. This is the basic compiler optimization that means we can have zero-cost abstractions at all. And because Rust is basically stealing C++ lunch here, we have the same problem. Here, what happens is we are using ND-array iterators. And for some unfortunate reason, the compiler decides that it does not want to inline the iterator stepping today. Instead, it just creates a separate function and calls into it. And because it does that, it loses all context about the situation in which the function is called, which has a very bad effect on performance. You lose, for example, knowledge of the window size. The compiler doesn't know anymore that this is about 3x3 windows, and performance is terrible. What do we do when we have this? If you ask compiler authors, what they will tell you is, okay, we have a tool for you. You take your function that's performance critical. You put a little magic annotation on it called inline. And then the optimizer will know that this function should really be inline, and it should not blindly decide not to inline it when it's important to performance. But there is just one problem with this, which is that in order to inline, to put this directive, you need to have access to the source code of the function. You need to be able to modify the definition of the function to add this directive. And here, because ND-array is a third-party library, that's not something we can easily do. So what we do then? We have three options. We can get in touch with the ND-array developers, get angry at them, say this function is critical to the performance of my application, it should really be inline. And then they will be telling you, but I have this other application that doesn't need the inlining, and if we put the inline directive, it will either result in code bloat or bad performance, because too much inlining is bad as well. We can apply random expert incantations learned from years of experience, messaging the code in such a way that the compiler has a higher chance of inlining it. Sometimes this works. I don't like this approach either, because it means that you've taken one code, you've gotten to another code that's logically equivalent, but now your colleagues must be aware that they must never get back to the old shape, even if it read better, because otherwise performance will drop. And then, there is unsafe. Here, iterators always involve unsafe code, because the whole point of iterator is to remove bound checks. And the way we do that in Rust is through careful use of unsafe code. So what we can do here is we can take the iterator from the array that fails to inline, and rewrite it ourselves in a better way. And we will put an inline directive because we know we need it, and then we'll get better performance. And when I did the last edition of this course, I thought this was the whole story. But I later figured out that I had forgotten about a fourth option. And that option is program profile-guided optimization. The idea here is you must now think about why the compiler did not inline the function. Compilers are basically, the optimizers are giant gambling machines. They are worse than CPUs in this respect. They take your code, they make a bunch of completely abusive assumptions about them through lots of coins, and they say, man, this should be in line, this should not be in line. There is one way we can stop the guessing, which is to put instrumentation in our code, which at runtime will measure statistics like how many times a function gets called, how long it executes for, which branches get taken, not taken, and then we feed back this data into the compiler. Know that the compiler has actual data from our benchmarks. It doesn't need to guess anymore. And it can apply the knowledge to make better decisions in areas such as inlining. And on the particular problem that I have here, it will resolve one case of missing inlining, improving performance by 80%, which is not bad for just tweaking our compiler or execution configuration, compilation configuration. So, something to know, in the next version of this course, this will be a dedicated chapter. I did not have the time to write it. Anyway, let's go back to last year. How did I find out first that I have inlining problems? Remember perf? Perf tells you what are your hot functions. In this sort of very tight computation, you should have only one hot function. If you see 3 hot functions, it typically means that you have an inlining problem where something should have been in line and was not in line. That's a telltale sign that you may have some black magic to do. By doing so, we realized that we have 2 problems. One is the next method of our iterator over pairs of elements in the Laplacian. No, sorry. Yeah, that's it. Pairs of elements from U and V. What we did at the time is we used flat iteration. So, you know, row major iteration over all elements. And for some reason, the compiler doesn't manage to figure out that this is worth optimizing. If you take your magic expert wand now and you start saying, no, I'm going to do a 2-pass loop, 1 over rows and 1 over columns, then the compiler can figure it out and you get the inlining you want. As I said, very unsatisfying, but you know, sometimes the sausage has to get made. And then we have the other issue, which is the zip of ND array that decided for some stupid reason not to inline when we really wanted to inline. And there we are stuck. I at least did not find any way to message the calling context in a way that resolves the inlining problem. So just for reference, the first problem is easy. You take flat iteration, turn it into a nested iteration, and it works. The second problem, at the time, I resolved it using unsafe. And this will stay in the course because what I discovered at the, after comparing this to the PDO version, Profile Guided Optimization version, is we still gain performance. Because in addition to resolving the inlining issue, what we also do is to write a custom iterator implementation that's tailor-made to our specific use case. And as luck would have it, in this particular case, our iteration is a bit too complex for the compiler to specialize the ND array code in the appropriate way, so that we get an optimal iteration pattern. And we can do it better by writing our iterator by hand, at the expense of course, unsafe. So lots of pointer handling and stuff that the C developers like. So this course is not about unsafe code, so I give it away to you. The point here is to tell you, sometimes people think Rust promises safety, but it has unsafe, so it's useless. And that's, you know, as they say in Star Wars, only the Sith think in terms of absolutes. If you can manage to get good performance by only having 1% of your code that is unsafe and must be manually checked, and everything else that's automatically checked, that's still a gain. That's so much less code that you need to manually check for presence or absence of undefined behavior. And if you do get it wrong and you get undefined behavior, you know where to look for. You grab unsafe in your code. These are the likely problem area. Saves a lot of debugging time. So let's start over from here. Try to integrate this iterator in your code. If your code is not at the previous step, which I expect, you can use the solution branch as a reference. And if you prefer to follow the previous steps instead, again, that's okay. Quality over quantity. You can still do it later, and I'll stay available on Discord to answer your question by the time you get there. Yeah.
Maybe you don't want to spend too much time on this, but how does the profile guided optimization stuff actually work? Like, how does the compiler pass information, I guess, back and forth over time?
Basically, you need to do two things. You need to acquire data. And then you need to pass this data to the compiler at the time where it compiles your program so that it uses it. You can acquire data in two different ways. One is to ask the compiler to add instrumentation in your code that measure stuff and write them to a file at the end. And the other way is to use something like perf to measure the data on an instrumented code. Here I'm using the first version because it's more portable across operating systems, more reliable, and usually produces better results. However, you should know that the perf-based version does have one advantage, which is that the instrumentation is much lighter weight, and you get a more realistic application profile because you don't slow your application by such a huge factor. Trade-offs.
How does it get injected in the code to instrument it exactly? Is it something that's automated, or do you have to write it?
Dash F instrument, dash something. Basically, the way I advise you to do it in Rust is to leverage the fact that we have awesome tooling in Rust, and you can just install an app called Cargo PGO, which will pass all the right flags to the compiler so that you don't need to know how this particular sausage gets made.
Thank you.
If you do want to know, pass in verbose to those build commands, and you will see the actual Rusty commands that get called. You may need, however, to install Cargo PGO and the LLVM tools first, because I added this part of the course yesterday, so which may be after you set up your environment. We have more course questions. It's just Romeo issues. Perfect. Well, not perfect for them, but perfect for me. Right. I know I'll be rushing you again, but yeah, one day. You know, people who do Rust courses actually normally take 3 days to teach Rust the language. Here I'm doing Rust and numerical computing in 1 day. That's the fun part. So, in the previous sections, I've been telling you how to optimize one aspect of code execution, which is vectorization, or SIMD. Single instruction, multiple data. We needed to take a quick detour through inlining issues because, you know, when your code reaches a certain complexity, the compiler goes crazy. That's life. But now we need to start focusing again on the other things our hardware can do, which we don't do yet. And here I'm going to focus on two particular things, which are fused multiply adds and instruction level parallelism. And as we're going to see, sometimes these things can be a bit at odds with each other. So fuse multiply add is a hardware feature, which most popular CPUs in high-performance computing these days, if not all, support. The idea is this. Before, your CPU was able to do multiplications and additions in SIMD if you want. And now, for the same price, it can do a multiplication followed by an addition without rounding in the middle. So, to sum it up, FMA, at least in theory, is both cheaper and more accurate. Sounds great, right? Unfortunately, as Vincent will hopefully get the chance to tell you in a minute, it's not always more accurate. It depends on what kind of computation you're doing. Because I'm more of a microarchitecture person, I will tell you about a different problem that we have when we start replacing multiplications and additions with FMA. Which is that, I look at my computation, I see, oh, multiplication, addition, here, multiplication, addition. Let's put FMA everywhere. What could go wrong? Well, how does 7 times slowdown sound in terms of wrong to you? That's bad. That's on a small problem size, to be honest. But even on larger problem sizes, it's bad. We still get up to a certain problem size, a 3 times slowdown, which is still not something we want in production code. So what happened here? Remember, our CPU has this powerful ability of superscalar execution, which is to say that if you give it independent operations, it can execute them in parallel with each other. And because all floating point units are available in pairs, this means that you can get a 2 times speedup for multiplications and additions if you have a mixture of multiplications and additions executing at the same time. When we turn a sequence of a multiplication followed by an addition to an FMA, we reduce the degree of instruction level parallelism available to the compiler. Because before we used to have independent multiplications that we could carry in parallel and only doing the sum at the end. And now we don't have them anymore. This turns our program into less of a parallel nice graph and more into a big serial dependency chain. And this is going to cost us performance. In this case, the 3 times slowdown. As I mentioned last time, when you run into this sort of thing, what you need to do is look at your code, find the dependency chains where you have one computation depending on the output of another computation, depending on the output of another computation, and need to break them down, which in this case will mean removing some FMAs on the critical path where we are not actually bound by the speed at which we do computations, but by the latency, which is the time it takes between when we ask the CPU to do something and when it's done. If we do that, we realize that using FMA at the end of the computation after the stencil is a big mistake. And if we remove that, we will get to the point where our performance is the same as before. Still not nice, but any progress is good to take. And the problem that we have here is that we have resolved the dependency chain at the end, but we actually still have it in the stencil. On each iteration of the stencil, we are doing a multiply add that depends on the result of a previous multiply add. So we have less instruction level parallelism, we have less superscalar execution, and because latency is a thing, we pay a price in terms of performance. What we will therefore need to do is to break the dependency chains of our Laplacians as well. And to get there, what we are going to do is this horrible stuff. I wish I had a better way to show you, but I haven't found one yet. What I'm doing here is I'm breaking down the 8 computations that compose my stencil into 4 parallel instruction streams. They each start with multiplication, that's the first step. And every step next is taken via FMA. when we do that, we now have 4 parallel instruction streams until the end, where we do need to reduce those by summing the intermediate results for U and V. This should improve our performance. And indeed, it does. We are now 2.6 times faster. That's nice. Can we do better? Yes. We can remove more FMA. Did I mention that FMA is not always a benefit? What we can do then is to start from 8 different accumulators, do the 8 things in parallel, and sum at the end. And we will need to use this sort of reduction tree for optimal instruction level parallelism. You may remember that from my architecture course. Compilers never reorder floating point operations, even if it's in your best interest to do so. And the reason why will be explained in the next talk. This doesn't help on my Intel CPU. It still helps on my AMD CPU. We will see why in the next chapter. So on Intel, nothing. I can tell you on AMD, 10% speed up. We are in the diminishing returns range, but still good to take. What happens then if we turn anything into multiplies and adds? You know, maybe FMA was a mistake. Yeah, I know. Some FMA can help. You just want not to add too much of it so that you still have enough instruction level parallelism to keep your superscalar CPU pipeline fed. As many things, it's a trade-off. So what about this Intel CPU that didn't get the same benefits as the AMD CPU, even if they should have roughly similar floating point execution capabilities? And here we need to invoke dark magic of the higher orders, namely the IEEE 754 specification for floating point operations. Let me tell you about the greatness that is subnormal numbers. When the IEEE 754 format was designed, we were in different days. People were extremely efficiency conscious when they wrote code. Every saving used to count. If you could save 1 bit of storage in your CPU register, even if it's a 32-bit register, this was considered a huge win. And that's why IEEE 754 designers came with what looked like, at the time, a great idea, known as the normalized representation. And the idea is this. Floating point numbers use a binary version of scientific notation. We have a number whose unit digit is non-zero, followed by a series of binary decimals. We multiply that by a power of 2, and we set the sign. If you think about it, in binary, there is only one possible number that's different from 0, and that's 1. Which means that if you go for that, you can only encode the fractional bit and assume that your leading digit will always be 1. That is, you always could if it weren't from one tiny but very important problem, which is that in mathematics we like to use the number 0. And there is no way to encode the number 0 using this sort of binary encoding. Now we have a problem. How did the IEEE 754 designers solve this problem? They added a special case. They say, okay, look, now we have a rule when the exponent bits are different from 0. But as soon as they start to be 0, the rule changes. And now we assume that the leading digits, it used to be 1 before, and now it's implicitly 0. And with that, if all of our fraction bits are equal to 0, we are able to encode 0. But it's actually better than this. We are able to have something called gradual underflow, which means that as a number gets too tiny for the exponent range, we can still keep some precision when we keep shrinking it. We lose bits of precision, but we still have some. And this gives you good mathematical properties that at the time the mathematicians who designed the standard thought was very important, such as the Stern-Benz lemma. There is just one problem. Saying that all zero exponent is spatial is irregularity. And I have said many times in this course that compiler authors hate irregularity, but hardware manufacturers hate it worse because compilers are software. You know, you need more complex logic, that's okay, we put more complex logic. CPUs are hardware. More complex logic is more transistor, it may be more pipeline steps, it may cause higher latency. So what did the hardware manufacturer do? They did not all do the same thing. And in the particular case of Intel, they decided to implement subnormal mathematics in an extremely inefficient way, which makes it 100 times slower than normal operations and floating point numbers. Now you may ask, when do we have subnormal numbers? When do these naturally emerge in our computation? Take an exponential decay series for a number. You know, you take a number, you multiply it by a number lower than 1. At some point, as it decays, if the decay is slow enough, it will enter the subnormal range. That's inevitable. Now, take spatial diffusion. Let's say you put some matter in your simulation, and you say that if the concentration is homogeneous, you start spreading it. Now, you still get exponential decay. It's in space instead of in time. So here again, you get subnormal numbers. Our Gray-Scott reaction diffusion system has both of these, so it gets twice the fun. And that's why we get performance on Intel CPUs that's much lower than what it should be. And in particular, we don't get improvements for superscalar execution that we would expect from experience with other CPUs, because the CPU is too busy processing a very bad subnormal math fallback that destroys superscalar execution due to how inefficient it is. So what do we do then? Well, thankfully, hardware people are not complete evil people. They have feelings too, which I like to hurt. And that's why when they do something so stupid as slowing down common mathematical operations by a factor of 100, they provide a way out of it. In the case of Intel or AMD, this way comes in the form of two flags in a control register of your CPU, which respectively allow you to ask the floating point unit to take operations that should produce subnormal outputs and make it 0 instead, and take an operation that receives subnormal inputs and treat these as if they were 0 instead. And when these flags are both set, basically you completely disable the handling of subnormal floating point operations, and you don't get the 100 times performance hit anymore. End of the story? Not quite. There are several problems. First, subnormal numbers, as again Vincent is going to show you in a minute, are there for a reason. They are not useless stuff. They are here because specific kinds of computations, like optimization problems, need them. Iterative computations need them. Or at least work better over a wider range of input parameters when you have them. If you disable them, you are going to break some computations. And unless you're a numerical analyst, you don't know which. That's the first problem. The second problem is that touching the CPU register is actually illegal in many programming languages. And the reason is that compilers, as I previously mentioned, love to make assumptions. In particular, they love to assume that your hardware is in the state that it is by default when you start your computer. If you start fiddling with hardware states to change it to a different value, your compiler will optimize code based on assumptions that are wrong, which can result in problems, also known as undefined behavior. So what do we do? In C and C++, we have one trick left that we can use. And that trick is fast math. which basically tells our compiler to assume that floating point numbers are real numbers and treat them in whatever way speeds things up, even if it completely destroys the accuracy of the results. Among many other things, this option will also disable handling of subnormal math. As you can imagine, it's also pretty dangerous to the numerical quality of your results, so you don't want to enable it in production. Furthermore, I mentioned compilers, but there is actually another undefined behavior character in our story. And that story, that character, is the C application binary interface, which is the protocol that your program uses when it calls any library on your operating system. In its great wisdom, your operating system most likely specified in its ABI that applications can also assume that the CPU floating point control register is in its default state. So you may fool the compiler with fastmath, but you cannot fool libraries. So you still need to be very careful when using this. There are still plenty of opportunities for undefined behavior here. So the Rust people looked at this, said nope, and for now do not provide an equivalent of fastmath. Which means we are kind of stuck, apparently, between two very bad options. The first option we can take is we say the high-level language does not help us. That's okay, we are going lower level. We take our whole computation, delete it, replace it with a big assembly snippet that sets the CPU register as we like it at the beginning, does all the computation in assembly, and sets it back to where it was at the end. No undefined behavior in assembly. But hopefully you can see why that is not a very attractive option. Or you can do what C++ developers love to do. You can say, yeah, undefined behavior is not that bad. I just made some experiment on my machine, and today LLVM has not destroyed my code. Looks like LLVM is not performing this optimization today. Hopefully it will not perform it tomorrow either. That's kind of like trying to argue with Darth Vader. I'm not saying that the compiler optimizers are from the empire of evil, but when the compiler is allowed to assume something, you don't want to break the assumption because mathematics is garbage in, garbage out. Reasoning based on incorrect assumptions can fail in arbitrarily bad ways. Still, let's say we want to make a deal with the devil. We can. Looks like this. Don't do it. What else can we do? We can have lots of different tricks, but these tricks are hardware specific. On AMD hardware, I think some of you know where this is going, you may observe that actually AMD ALUs are completely weird, and they take a performance hit when you multiply numbers, but not when you compute a fuse multiply add. Ask AMD engineers what they did. I'm not sure I really want to know. But what this means is that if you replace A times B with a fuse multiply add of A with B and a net end of 0, you remove the overhead associated with subnormal numbers on AMD CPUs. There are just two problems. First, any clever compiler optimizer knows that this is equivalent to this. There may be some implications in the IEEE standard that they have not fully thought out that might prevent this optimization, but otherwise your compiler will helpfully say, hey, when you are doing an FMA with net end of 0, let's go back to multiply, it has lower latency, it's better. First problem. Second problem, remember, this is mainly an Intel issue. AMD does have some subnormal hits, but it's more like 2 times in the worst case, not 100 times. We really want to fix the issue for Intel, and for Intel, this trick doesn't help because their FMA is just as broken as the multiply. So what do we do then? If you are someone from the signal processing community, you may say, hey, real-world signals are always noisy. I can add a bit more noise to my signal, no one will notice, and it will keep it outside of the subnormal range, at least statistically speaking, if the noise is of the right magnitude. That works for signal processing people. It's somewhat unsatisfying because, you know, adding random noise degrades to some degree the precision of your computation. And you need to be very careful with it because generating random data is not free and can very easily end up costing you more than subnormal math if you do it too frequently. So you need to find just the right step in your program where the random noise should be inserted in order to fix the problem, hopefully not adding too much other overhead in the process. So not a super satisfying plan indeed. What else can we do? Well, you know, the compiler knows how to flush subnormal to 0. Well, the CPU knows how to do this, but we can do it. You take your CMD vector, go over elements one by one, check if it's close to the subnormal range, and if so, take it to 0. If you remember my architecture talk, your eyes may start to be dripping blood. That sounds very expensive. If you use your CMD instructions in a clever way, you can take it to an overhead of 4 instructions, which is not great, but something people can live with if you don't do it too often. It's certainly much less expensive than doing the random trick. Or, you know, there's always this last option where Intel could fix their subnormal math, maybe someday. I don't know. Every other CPU manufacturer I know of has managed to find a way to have subnormal math that's like maybe at most 2 times slower than the normal math. I don't know why on Intel specifically it's so bad and why they have not fixed it in like so many years. But you know, good luck telling a hardware manufacturer that their hardware is buggy and must be fixed. So what I propose you do is for this part is you start with the deal with the devil, because currently at the time of writing, LLVM does not exploit this particular undefined behavior. And you see how much performance you can gain for it. Then you immediately remove this curse code. And you start using the flush to 0, manual flush to 0 approach that I've shown. And you see, you know, considering the overhead, how close does it get you to the deal with the devil? And then you'll be able to decide for yourself, is the performance that you still lose worth the deal with the devil or not? Are there any questions on this? There's something on Discord. What? Yeah. By the way, I keep asking all the time. People may think I'm speaking to the room. Again, I'm speaking to all of my students. If you're remote, it's not because you're remote you're not allowed to ask questions anymore. Please ask questions. If you're stuck, say so. Say why. Maybe I can help. I mean, that's kind of what I'm here for. And then we'll get to different kind of curves, but that will be a story for later. So we've been following some progression in this second part of the course. We started with some optimizations that are kind of at the logical level, that are, you know, knowing your language well, in this case Rust. Then we started going into hardware optimization. That worked well. We saw, you know, you can get a vectorization speedup by doing things a certain way, and you can get a better vectorization speedup by doing things in another way if you manage to solve the inlining issues that your compiler may throw at you. Then I started getting into the realm of optimizations that do provide a benefit, but the benefit starts differing across hardware. So here we start feeling the law of diminishing returns, you know. And this is why I have decided to, for the sake of honesty, conclude this course with the optimizations that didn't work at all. I think that's important because hardware manufacturers like to make you think, you know, you're going to optimize your code. It's going to be amazing. You're getting 32 times speed up, no effort. Just rewrite your code in this particular way or use this particular compiler. It will work great. And that's actually not true. I mean, this course is years of preparation work. And I mean, part of that is, figuring out how to make containers work inside of a runtime as broken as a container. But the numerical part also took some time. So first optimization that didn't work, cache blocking. Here, I'm really bitter because Sebastian tried it too, and he managed to get it to work. And now I feel pressure to find a way to get it to work at some point. But, for now, I have done it in a particular way in this chapter. It does not improve performance in any way. In fact, it degrades it by 10%. Whether you're running in sequential, parallel, same thing. No idea why. I need to spend more time researching this to figure it out. But just for the sake of argument, the general idea is this. Let's go back to scalar for a minute because that's easier to visualize. When I go through my computation, output cell by output cell, every time I'm loading data from all the blue squares in the schematic and also the red square in the center, and I'm writing data to the red square in the center. This means I'm interacting with memory. And as we have seen, RAM is horribly slow. So we really want to do that using CPU cache. So how would a naive CPU cache handle this particular pattern? It should work that way. So in purple, you get expected cache misses, which are the situations where the CPU looks for data in your L1 cache, doesn't find it, so it needs to load new data. For the first data point, that's true of all inputs you access, and also true of the output you access. By the time we get to the second data point, however, you may notice that these memory cells that we're accessing are the same that we accessed last time, which means they should still be there in CPU cache. So here, our CPU cache should start doing its job and help us only load 4 floating point number times 2, because we are computing U and V, instead of loading all 9, which would be very bad for performance. The question is, what happens when you go to the next line? In an ideal world, you would like to have this. So your CPU cache still remembers which data you're accessing. It remembers that you accessed these squares in green last time, so it doesn't need to load them again. And then, as you move over the second line, you only need to load one new input per input array, which is great for memory access performance. If, however, you have too long an image line, this will not work. What you expect instead is that your CPU cache by then will have completely forgotten that you initially loaded the first data, and then you get a copy of the previous one. So more memory loads from lower level cache or memory in the worst case means, in principle, worse performance. By changing your loop in a very weird way, which is called blocking, we saw that earlier, you should be able to get to the scenario B by doing this sort of thing. So here you have a first block. You generate this data, this data, this data. You go to the next line immediately. You don't go through the full line. And if your horizontal size is well-tuned, which I show what to do using some theory, you should get data that is still resident in cache. So scenario B, better memory access performance. Yeah.
So the idea is that you experimentally figure out how long you think it's in the L1 cache, and then you do it.
You can do it experimentally. You can compute it theoretically. It's easy in this case. Okay. But if it's theory, you need to make some assumptions. Like you may need to assume your cache is least recently used, that the peripheral behaves in a certain way. So theory is not always right, but it should get you close to the right order of magnitude, and then you can tune to find the optimal value. And that's what I tried to implement, and it didn't work at all. I don't know why. Something for the next edition of the course. Yeah?
You tried with a larger problem also? Because with a small
yes,
one,
and I don't think it helped either.
okay. Because with a small one, it's a bit normal. You don't see anything.
I have no idea what's going on. I need to spend more time on it. And then, probably due to this, I also get issues with parallelism where the code scales badly in parallel. Most likely because since my memory access pattern is not as optimal as I would like to, now my memory accesses, too many of my memory accesses will be going all the way through my memory. And then I become bottlenecked by the resource which is shared between all my threads, which is main memory bandwidth. And then we expect poor scalability. So, something for a future edition of this course to do, figure this out. If Sebastian could do it, I should be able to do it. Otherwise, I'm not bottlenecked by what I think I'm bottlenecked by, which is the hypothesis of Pierre that I also need to investigate. To conclude, this, I think, was a good enough introduction to numerical computing in Rust. It tried to address the challenge of explaining both Rust and numerical computing optimizations in one day. I hope you were satisfied by it, and some self-study will make you even more satisfied by it. We'll see. Feedback welcome. If anything isn't clear, feedback especially welcome. If you struggle with anything, because that's how the next edition of the course is going to improve. Is it people report what they're struggling with. What I would say about Rust today is I think it's a bit of an interesting spot compared to C++, which, to be honest, is its main rival. They have similar ideas. They are competing for the similar region of the HPC problem space, you know, high-level abstraction, low-level performance. Some things are much better, iterators, multithreading. Other things are similar, SIMD, ND-array, ILP, not much better in one language than another. And some are worse, as you will see next week. In my opinion, GPU programming right now is not at the level that it should be in Rust compared to what it is in C++. What I would say, however, is that in my opinion, people sometimes, when they think about language maturity, tend to have a bias where they think too much about language features. And there are some desired language features in Rust. You know, people would like to have stuff like variadic generics, better const generics, that sort of stuff. But what I would argue is that for the kind of computations we're talking about here, finite difference systems with Laplacians, that's not the problem. What we need to get the language to a state where it's more competitive with C++ is better libraries. And that means people working on libraries. So if this course convinced you that Rust is something worth investing in, my advice would be do not write only applications. Write libraries. Share them with the world. Writing a library is one of the best ways to know more about a language, because libraries have problems that applications don't have, like the floating point genericity problem I mentioned earlier. So solving these problems will make you a better programmer in any language and improve the ecosystem as a bonus. Let's say you saw this as interesting and you want to know more. In the interest of fitting this course in one day, I cut a lot of corners in Rust teaching. I did not spend a lot of time explaining darker areas of the language, things like generics and traits, lifetimes, async, unsafe. There's a lot to learn here. And two books I would recommend, depending on where you stand in terms of programming, is the official Rust programming language ebook, available for free on the web. You can also buy a printed copy from O'Reilly. It's, I would say, more targeted to people with low familiarity with this language family of Rust, C, C++, Fortran. It does quite a good job at introducing the language, and it's always the most up-to-date book you will find because it's maintained by the Rust language teams. if you, like me, you have some existing C, C++ Fortran experience, this book will likely be a bit slow for you. You would like, to go faster on the stuff you already know about, like stack versus heap, that sort of stuff. And you would like to spend more time on how the Rust pointer aliasing model differs from that of Rust, for example. That sort of hardcore low-level stuff. In my opinion, the Programming Rust book by Jim Blandy is a better pedagogical resource if you are in that category. These two are for people like me who are more, theoretically minded, who like to spend a bit of time understanding how the language works, why it's designed the way that way before they start writing code. Some people do not learn like this efficiently. They prefer to, experiment a lot, throw things around, see what happens. There are courses which are better suited to this audience, such as Rustlings and Rust by Example, which you can also check out. Once you get relatively comfortable with the big picture of the language, then I put a bunch of links to reference documentation that you will need for everyday Rust practice. And for this course, that will be the end of it. So next week, I will show you a bit more about how GPU works. But for now, I thank you for your attention, and we start taking the last questions. Silly question, but nevertheless, how popular is Rust across the various STEM fields today? Depends on the STEM field, as usual. It's starting to get very popular in the embedded sector because people realize that having a low-level language with an async await model that actually works without allocating memory is super helpful when you are on something like a Cortex-M that's basically interrupt-driven. It's a very natural fit for this sort of hardware reality. And you can get some, let's say, minimal scheduling layer that gives you all the cool things you would normally do in embedded much more easily than you would in C, for example. In security, it's also getting popular because security people want no undefined behavior, as they know that that's responsible for, I think, a third of the vulnerabilities in all popular programs. In numerics, it's younger. People are trying stuff out right now. There is no new conference yearly, a numerical scientific computing in Rust. They show some interesting things. You should check it out. But the library ecosystem being a bit young tends to put people off, and also the choice of an unusual language, and that's reasonable. Which is why this year the language team has finally voted a long-desired high-priority language goal for the next years, which is to improve the interoperability of Rust with C++. C interoperability is easy because every language in the world was designed to interoperate with C, and C is not that complicated of a language. C++ interoperability right now is something that only C++ achieves. That's for technical reasons like templates. To instantiate a template, you need to have a C++ compiler available, which means that now you need to put a C++ compiler in your Rust compiler, and you can see how that can be complicated. And there are also more, people maybe have not thrown enough effort at this problem yet, and maybe with some kind of compiler plugin, this could be improved. We'll see how it gets out. I'm personally quite excited. One thing I will point out in terms of STEM is there is one particular area of numerical computing where Rust has started to take off quite nicely. And surprisingly, that area is Python libraries. R libraries as well? This I didn't know. Cool. So why, you may ask? And the reason is that interfacing languages is hard. And as I mentioned, interfacing C++ with anything is hard. For years, the Python people had a choice. You write C, not very exciting. C++ with a C interface, not that exciting either. Fortran. How do you even do that? And basically, what Rust has provided is high-quality binding tools to easily expose Rust logic to Python and vice versa. And because the Rust community has a huge expertise in building high-quality build infrastructure and language tooling, it's much easier to build and package Python plugins that are written in Rust than it is when you are using C or C++, for example. And the Python community is especially sensitive to this. And they are also sensitive to the other aspect, which is that in the eye of many Python programmers, Rust is easier to learn than other currently existing languages for numerics. So, you know, if you're living in a Python bubble and you don't need to interface with the C++ library world, it may be a really good choice for you. Any other question? If not, I guess I will. Oh. Yes.
When I'm starting my next project, why should I consider starting it in Rust? Or maybe what should I consider when deciding whether I should start in Rust?
So as always, when starting a software project, the main factor that will intervene in language choice is what other languages you need to interact with. If you need to bind with lots of C, the main issue you will face is knowledge of Rust in your team. It's not the hardest language to learn, but you may expect some ramp-up period, like 1 or 2 months before people are fully effective in Rust. That's something to consider if you are already on tight time delays. In exchange, all large-scale Rust adoption experiments at Google, Amazon, Microsoft show that once people have gotten up to speed to the language, they find themselves to be about twice as effective as they are in C++. In terms of how many features they manage to put in a day, how many bugs they introduce. Overall, it's always about a factor of 2.
No, I didn't see you mention anything about consts.
Yes.
Is on purpose or they don't exist? Or?
It's part of the language that I consider too complex for a one-day course, along with the rest of generics.
Okay.
Const in Rust is, you can think of it as the combination of constexpr and consteval in C++. The basic idea, and non-type template parameters as well. So as usual, we have taken 3 C++ features with completely unrelated interface design, and we have put them into a cohesive role. The idea of const is that it allows you to do things like, data structures that are generic over the length of a SIMD vector or array without dynamically allocating memory, with correct compiler knowledge of things like alignment. And that's very powerful. In exchange, what you get is a more difficult programming model, because now your inputs must be known at compile time. And for reasons that I will not get into today, it's difficult. Basically, you can put a complex const expression in the const parameter of a function of struct, but that function cannot, in turn, pass by a more complex expression to another function in the const parameter. That's linked to a compiler limitation that people are trying to lift as we speak.
Okay.
In exchange for that, you get rid of the constexpr consteval distinction, which I have always thought was one of the most stupid things about C++ constexpr. For those who don't know, first, consider yourself lucky. Basically, constexpr represents the fact that if the stars are correctly aligned today, you might be able to compute value at compile time. There is no compiler guarantee that the value will actually be computed at compile time, no matter what people think is the case. Check the language standard. That's why C++ had to introduce constable, which is the bug fix for constexpr that make it do what people think constexpr does. But constexpr was not designed for that. Constexpr was designed for things like, sizing arrays based on complex expressions. It's not at all designed for improving performance by computing more at compile time. which I should say is something that compilers were already doing in the days of Grace Hopper. You can find a very nice paper, a catalog about optimizing compilers, transformation, I don't remember the exact name, which already explains the optimization of const propagation, which all your compilers that you use on an everyday basis already know to do today.
What are your, do you have a set of language features or top RFCs that you're following right now for things that are going to be added to the language soon?
Again, in my opinion, the libraries are more of a problem than the language right now. But I'm curious what the variadic generics people are going to do. This would unblock some things, especially GUI, which has been a problematic area in Rust right now. And I would like to have more expressive power when using const expressions. As I mentioned, there's currently a compiler limitation that prevents you to do this. Because then I can start doing fancy small matrix operations in Rust, and I can show the eigen guys who don't know how to implement this correctly, how it's done, but in a different language.
Can we use MPI with Rust?
Yes.
With Rust?
There is a high-level binding to MPI. Never tried it because, as I mentioned previously, I mainly work on single node performance matters. But I've seen people say they tried it and they were OK with it.
Thanks.
People are trying to do fancier distributed system things, more like what HPX does in C++, for example, but that's very mature right now. I would not recommend using that in production.
Yeah, maybe I missed it, but we talked a lot about vectorization, but nothing about actually parallelism.
Yeah, it's at the end, in the things that didn't work category.
Okay.
Which I think is because of the data blocking problem. And I hope, if I solve this one, I will resolve the other one. Yeah.
For the blocking, you used some square or some rectangles?
I cut lines only. From the theory I've shown, I believe this should be sufficient. True, you do lose one little edge of floating point at the boundaries between strips, but I don't think this should matter because you only do this loss when you've gone through a whole vertical slice of the matrix.
But it means that if you have two threads, Nightbow, how the work is dispatched? I mean, the first thread is taking the first block.
So I do recursive decomposition. So first, I do thread blocking by lines. I cut my domain by lines to distribute across threads. And then within a line, I cut by columns to do the L1 blocking, L2 blocking.
Because I'm following the blocks over the line, so I still benefit from the prefetching in some ways.
Yeah, that's another thing I would like to try at some point is explicit prefetch instruction.
Yeah.
More hardware black art that may or may not work and will likely not work, but you don't know until you try it. I mean, it did provide a very nice performance improvement on another project of mine, so it's worth trying.
A lot of simulators like provide support for Python and C or Python.
Yeah.
Do you think some of them will like start?
There is some uptake. I'm not able to predict the future, so I can tell you if it's going to explode or just stay relatively niche. We'll see.
We'll see. Okay. We talked a lot about cache blocking these days, but there is also probably not this is the term, but you could also have a variable like stuck in the register directly.
I already do this.
Uh-huh.
I already do this. More precisely, the compiler does it for me, and I have checked the assembly does it well.
But you have to, like, this is only in some specific cases where your computation allows it, but how did you do that? Can you show?
What does the code look like? This, I don't need this. Right. So what do I have here? So I'm not sure how readable this is going to be on the projector screen, but right now the sequential part of the code takes a block of inputs, blocks of inputs, blocks of outputs, and it does some further blocking for the L1 blocking purposes. So yeah, it slices the input blocks the way they need to be sliced, at least the way I think they need to be sliced. Then I have my custom iterator doing the joint iteration of our input windows and output values. And within that, what I do is I just put the stuff I need to be in registers in global variable, which is a very convenient trick that will almost always solve all your compiler register locality problems for you. Here, I'm actually doing it also because it makes the code clearer. But I've seen in different code that compilers are not that good at keeping stuff in register if it comes from memory. Even if we are in Rust, we should have automated restricts. The implementation of restricts in LLVM is so broken that sometimes LLVM would be perfectly within its rights due to the restrict semantics to keep stuff in register, but still it wants to spill them in memory way too frequently. The way that happens, you can work around it by using more local variables.
Like just different variables.
You do your load at the beginning of your loop body, and you save it at the end. I have quite a few questions on Discord. I would like to get to those as well. So yeah, someone mentioned that one particular example of a library that's popular in the Python ecosystem is Polars, which is basically rewriting pandas in Rust and claiming nice performance benefits over the current pandas implementation. Maybe this will start a performance race. Maybe the pandas people will give up and say, use Polars, it's faster. We'll see. What I will say is you should not, among C, C++, Fortran, Rust, pick a language because you think it's going to be faster. Programming languages can make it easier to have faster code. They can, hint you into the fast code direction. And I believe Rust does this personally. But if you know what you're doing in any of those languages, you have a performance limit, which is how fast your hardware goes. And given enough effort, you will be able to reach that limit. It's just the amount of effort may vary. Am I right to say benchmark for this sum is bad? I want more context, which machine you are running, what did you get in sequential mode, how is it now, which optimization you have applied. There's not enough information right here for me to tell you if it's fast or not. I could probably do some quick theoretical computation to check if the order of magnitude sounds right, but really I want to know what CPU you are using and what you've tried so far. And with that, I see Vincent getting very eager to show you the end of the story that I started showing you about how much of a pain floating point math can be.